you know what? Just for the sake of making sure that even the people who refuse to ever ask questions see where the review material is. If you get to the course webpage, you will see under Monday, October 14, a review day for the FOSS midterm. There is a PDF posted there which has a bunch of review questions for said midterm. They're sorted by topic, so as you go through it, if there are particular problems you're struggling with, that even tells you what topics you need to refresh yourself on. So go through the textbook sections on those, go through the notes I have on those, maybe go back through the WebWork problems on those, corresponding to the sections that you struggle with the most. If you already know how to do everything, then that's probably not where you need to focus your time. Cool. So let's talk about exponential functions. And I think the right way to begin is just with an example of these things come up in nature all the time. Let's see one of them. So here is a situation, radioactive decay. So the unstable radioactive isotope americium-240 has a half-life of about 2 hours. Yeah. God damn it. Yeah. Yeah, you should. All right. These here are going to make their way back. I'll just serve the back and walk my way forward. Oh, I see. It's not counting, it's basic observation. Cool. Now, this radioactive isotope has a half-life of about 2 hours. And in fact, well, prepping for this, I noticed there was an inconsistency. There's a lot of instances of days written, or I'm pretty sure it should be hours. And this makes me think that I made an error, in fact, while designing these notes. Now I'm not 100% confident whether that should be days or hours. Anyone just know off the top of their head? All right, fair enough. It is like an unstable and absolutely artificial isotope that is only lab made, not naturally occurring. But this is bugging me, so I'm going to look it up. There we go. This should have something. Oh, come on. I've got to have half-life on this page. 241. Those are really long. I might be wrong. That's okay. I'm not a chemist. This isn't a chemistry class. Let's take that 2 hours as law, because the notes are built around it. So what does a half-life of 2 hours mean? That means if you start with any sample of americium-240 and wait 2 hours, half of that sample will decay. And the particle physics of that is americium is an unstable element. It wants to decay in any 2 hour time frame. A single atom of it? Yeah. Is going to have a 50% chance of decaying, so because most samples are a great many atoms, half of it does decay in any 2 hour time slot. So if you start with 1 kilogram, then in 2 hours time, half of it will decay. You'll be left with 500 kilograms left. You wait another 2 hours, you'll be left with 250 kilograms. If you wait another hour, half of that will have decayed, leaving you with, let's see if we can divide by 2. 125? Oh, I'm saying kilograms when I mean grams. If you wait another 2 hours, at time equals 8, another half of it will decay. Gosh, let's see. leaving you with about 62.5 kilograms. Grams. No, you start with 1 kilogram, so 1,000 grams. If you wait for that 10th hour to have passed, you'll be left with that divided by 2. Gosh, is that 31.25? In general, if you wanted to know how much of this substance is left after 2 times n many hours, how would you get that? What would you need to do? Well, you need to divide by 2 a bunch of times, right? So let's write that down. If you want to get the amount remaining after 2n hours, well, n many half-lives have passed. So you start with that initial quantity, and then you need to divide by 2 a bunch of times. Oh, Chris. Cool. That feels pretty okay. So maybe let's just make one quick computation. I don't know. At time equals 26 hours, how many times do you have to divide by 2? 14 of them? All right, 26 is 2 times 13. So, we'll do that the long way fast using a machine. I'm not going to do that manually. I count up to 13 correctly? All right. So you get what you get. You get around 12 1/100ths of a gram, 12 centigrams, I guess. So on the one hand, that's not very many. That was also a pain to type, right? So you there's a mathematical shorthand for multiplying by something a bunch of times, and it is.
Put it to the power of n.
Yeah. Well, I guess it would be n over 2. In this case, raise it to the power of 13. However many 2's you want in a row. Cool. So I did count 13 correctly. Feel okay so far? All right. Well, not every number is even. So, what if instead I want to see how much is left after just 25 hours? How many times would you need to divide by 2 to get to 25 hours? Well, I guess 12.5 is the right idea, right? 12 and a half half-lives have passed. Because that's 25 over 2. And in fact, that's exactly right. So, at 25 hours, 25 divided by 2 many half-lives have passed. So you need 1,000, the initial quantity, divided by 2, so that 25 over 2. Parentheses matter. That is about 0.17 grams. That feel pretty okay? In general, if you wait n hours, what do you need to do to know how many half-lives have passed? Well, n over 2 many. For every 2 hours, 1 half-life passes. So if you wait n hours, n over 2 is the number of half-lives. So you'll end up with 1,000 divided by 2 2 to the n over 2 grams remain. All right. That feel pretty all right? So, next one I think I want you to do, this is definitely a thing that is going to require a calculator. Do you think you could figure out how many are left at time equals 5 hours, 42 minutes, and 3 seconds? Well, let's talk through. So we need to know how many half-lives have passed. So that means we need to know how many 2-hour time intervals have passed. I guess that means that I want to convert all of that information to hours. So how many hours is that? How do you compute how many hours that is? Let's start with the 32 minutes. How many hours is 32 minutes? 0.5333. That sounds right. How'd you get it?
Divided 32 by 60.
Divided 32 by 60. So let's start with that. 32 minutes is the same thing as 32 minutes times 1 hour per 60 minutes. Because right, 1 hour is 60 minutes. And you say that's around 0.533, probably a repeating sign on that. All right, I feel pretty good. How about 3 seconds?
3 divided by 3,600.
Nice. So 3 seconds is, let's see, how many seconds to an hour? Well, it's 60 to a minute, 60 minutes to an hour, so I guess you multiply those to get 3,600 seconds to an hour. So 32 seconds times 1 hour is 3,600 seconds. And you actually do that division, and well, I don't know how many people did that division already.
0, 0, 0, 8, 3.
Cool. All right, so we have enough information now to convert this to hours anyway. It looks like this is 5 plus 0.5. I think we can round to the thousandths. We don't want to be that precise anyway. Plus 0.000. Let's see, if we're rounding to the thousandths, that would just round up. So that's how many hours have passed. If that many hours have passed, how many half-lives have passed? How do you get the number of half-lives that have passed?
2.5.
About 2.5 half-lives, because like every 1 hour is half a half-life. So divide that by 2 to get the number of half-lives. So all that was computing the time passed. Let's figure out the number of half-lives. To get that, it's about 5.534 divided by 2. Every 2 hours makes a half-life. And do that division. Let's go out to the thousandths again. What do you get? I mean, I agree, it'll be somewhere around 2.5. All right. If you now want to know the quantity, it's that 1,000 grams divided by 2. Well, this is all approximate. to the 2.767, which again will be approximate. Well, you all have the calculator out already, so I don't want to do it.
From 146.9.
Cool. That seem reasonable enough? And I think it even matches up with the table pretty okay. 5.5 hours is just a little bit less than 6. So you won't have quite gone through 6 half-lives left, so you haven't gotten quite down to 125. Yeah, 147 grams seems sensible. How's that procedure feel? Nice. So, what's the point of exponential functions? So we have like this definition. So exponential functions generalize the idea of multiplying by a number over and over again. And you can, it's a generalization because what does it really mean to multiply by 2.767 many times? Right, we'll have to make sense of that in order to really make sense of what this means. But the idea is to capture any sort of behavior that behaves like iterated multiplication. And we'll write it down on the next page then. So what are exponential functions? So an exponential function is anything that looks like a base to the power x. And let's just say some things we already know. If you raise a base to an integer power, b to the n just means b times b times b dot 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 times b n times. Gesundheit. So just like how when you multiply a number by n, you add it to itself n many times. If you raise something to the n power, you multiply by itself n many times. You can raise something to a negative power. In fact, we probably should have on the previous page. Let's think about what that should mean. So when you raise something to a power, you multiply it by itself that many times. Raising something to a negative power should be like the opposite of that. So what's the opposite of multiplying a number by itself a bunch of times? B to the negative n is the same as dividing by b that many times. So you can write that down as 1 over b to the n. Or you want to divide by b n many times, that's how you do it. Or 1 over b to the n. Both of those mean the same thing. That feel pretty good? So in fact, on the previous page, which of those, like that's exactly what we did on the previous page. So we could have instead written that as like 2 to the negative n over 2 instead of dividing by n over 2. The 0th power. So when you raise something to a power, you multiply it by itself a bunch of times. So let's try to figure this out. So what do you have left if you multiplied by b no times? I think 1 seems reasonable. And let me tell you why I don't want it to be 0. So like, b to the n is supposed to be what you get when you multiply by b a bunch of times. B to the 1 should probably be just b, right? Multiply by b once, that's what you get. But that should be the same as multiplying by b 0 many times and then multiplying by b once. And if you set b to the 0 to be 0, you don't get that. So I'll set b to the 0 to be 1. As long as b isn't 0. I won't even try to define what 0 to the 0 means. Because if you try to make sense of what 0 to the 0 means using different velocities, you can get absolutely any answer you want. So it's just not defined. Rational powers. So you'll notice on the previous page, I needed to be able to put a rational number in the exponent, right? Like 2.62 was the number I needed in the exponent, something like that. 2.562? Doesn't matter. That means I need to know at least what it means to put a rational number in that exponent. And what does it mean? If p over q is a rational number, then b to the p over q is what you get if you take b and raise it to the pth power and then take the q through it. That's all. That's what it means. That's not how the computer is computing it. The computer is doing something fancier. It's using what's called a Taylor series. But that's a way of making sense, at least in terms of what the thing means. So, let's do this to use this to make some computations. Some of these we'll be able to do on the nose, some of them not. I think all but that last one we'll do on the nose. So, what should 2 to the power 3 mean? I want 2 answers. I want what it means and what it, number it's equal to. So what does it mean? Say it louder.
Where?
Yeah. Cool. But why is it 8?
It's 2 times 2, which equals 4, and then 4 times 2.
Nice. Yeah, I agree. What about 4 to the power of negative 3? What does that mean? Yeah.
4 divided by 4 divided by 4.
Almost 1 divided by 4 divided by 4 divided by 4. So you don't start at 4 because 4 is like 4 to the 1. You want to start at 4 to the 0 and then do a bunch of dividing. So there's what it means. And then if you want to know what that is, I guess you have to multiply the denominator as 4 times 4 is 16, 42, 64. How many people just know some of their powers of 2 up to 1,024? Oh, no computer scientists here? All right. Cool. 8 to the power 5 over 3. That's another one which, in this particular case, you can do on the nose without a machine, using the definition. So what is it that should mean?
The cube root of 8.
Yeah, so it'll be the cube root of 8, and then you raise it to the power 5. And what is the cube root of 8? 2. 2 times 2 times 2 is 8 because of the line right above that. All right, so I just need 2 to the 5th. And 2 to the 5th is what? 2, 4, 8, 16, 32. All right. And finally, the last one we can't compute on the nose. If I asked you to compute Euler's number e raised to the power square root 2, well, this one you can't do on the nose just by hand. You have to do something approximate using a machine. So tell me, what is e raised to the square root of 2? I guess those of you with calculators can get it done too. Let's also just do it. Euler's number e raised to the square root of 2, too many parentheses, is about 4.11. And that last one is just to point out that there are some computations that in this class we absolutely just will not develop the tools to do on the nose by hand. And in fact, this definition that I'm using right here can't apply. Square root of 2 is not rational. I haven't told you what it means to raise a number to an irrational number. If you want to make sense of those, really you need the technology called Taylor series, which is something that's built on top of calculus. Anyone have Calc 2 in their major path that they know of right now? Cool. Taylor series are a really powerful tool that comes up in Calc 2 that lets you do all of this. Every computer-based computation of anything that's complicated is probably built on top of the Taylor series underneath of it. All right, cool. So we have these things called exponential functions. So we have this new function that we want to study. And you know what I like to do once I have a function definition? We're going to see what the graphs look like. So let's pick the simplest base I can think of for this. Let's pick base 2. Let's try to graph this thing. So, doing that, what's 2 to the power 0?
1.
1. Anything to the power 0 is always 1. I'll put that on the graph. I have specifically chosen these grid lines so that this fits. 2 to the power, let's see, I think I'm going to do the positive powers and then we'll do the negative powers. 2 to the power 1. 2 to the power 1 is 2. So when x is 1, I'll plot 2. 2 to the power 2. Nice, so it's twice as tall. So there's 1, 2, 3, 4. 2 to the power 3. Again, twice as big. It's 8. So there's 1, 2, 3, 4, 5, 6, 7, 8. 2 to the power 4 is double that at 16. So there's 8, 9, 10, 11, 12, 13, 14, 15, 16. All right. So we notice some pattern, like this exponential thing seems to be growing really fast as the input grows. Even by the time the input was 4, the output was 16. By the time the input is 10, this output is going to be over 1,000. Negative powers. What's 2 to the negative 1? Which maybe I'll put as 0.5 just because that helps me to tell like how big it should be. 2 to the power negative 2. 0.25. A quarter if you prefer. 2 to the power negative 3.
0.125.
Awesome. And like it's getting to the point where like I can't tell that it's not 0 at the scale that I draw because of the big fat dots I'm drawing. 2 to the power negative 4, divide by 2 again. I think that's 0.0625. And as is standard, I'll like interpolate between to see what shape I get. Nice. So there we see the graph of the exponential function with base 2. And you know what? Since we have this graph written down now, like, what are some things you notice about this graph? What's some behavior that you see? Is it even or odd? Nope, not at all. Any other buzzwords that we've said in the past that you see? What's its domain? Negative infinity to infinity, all real numbers. What's its range?
0, not
0, but not including
Yes,
0 to
not
infinity. You can't divide by 2 enough times to get yourself literally to 0. You can get close. Does it have any asymptotes? No vertical asymptotes, no slant asymptotes, but it has a horizontal asymptote, right? Horizontal asymptote at y equals 0. The horizontal asymptote is only on the one side, though, which is different from rational functions. So we can notice lots of things by looking at the graph. Let's start stating some of the algebraic laws that exponential functions follow. So let's start with this. Let's simplify that. 4 to the 7 times 4 to the 2. Let's just write down what that means. Yeah.
That would be 4 to the 9th.
I think it is 4 to the 9th. But why?
Because it's the same thing as still 4 being multiplied by itself 9 times, or 7, or 2.
Yeah. I like that. That forced 4 to the 7th. Let's color code even. That forced 4 to the 7th is 1, 2, 3, 4, 5, 6, 7. Put the multiplication symbols in between so you don't think I'm thinking of a like 7-digit number that's all 4s. Times 4 times 4. And I put those parentheses in to emphasize that that's the way that they're grouped, but are the parentheses necessary? Do they actually do anything? Multiplication is associative. So yeah, that's just 9 fours all written down. In fact, there's a general rule there. If you have any positive base b, I'm going to demand that my bases always be positive. Otherwise, you get some weirdness about negative numbers or zeros showing up. And any numbers x and y, then b to the x times b to the y is always the same as b to the power x plus y. And you can use that both ways. So whenever you see two exponentials written next to each other with the same base, you can add the exponent. And sometimes it's useful to say, I don't want to have this complicated thing in the exponent, but it's just a bunch of stuff added together. You could rewrite it as a bunch of stuff multiplied. And maybe here's the most obvious application. 3 to the power 3 halves, I have no way of computing manually on my own. I'd have to use a calculator because I don't know a square root of 3. 3 to the power 5 halves, same issue. I can compute that product though without a machine. Because, are those both the same base? Mm-hmm. Cool, so I can add the exponents. So this is the same as, switch colors, 3 raised to the power, and you know what? I feel like my hand's just shaky enough that a small exponent is not going to be readable at all, so I'm going to write it the way you type it into a calculator. You write it the way you want to write it. I'm just not feeling good about my penmanship right now. 3 raised to the power, 3 halves, plus 5 halves. Feel pretty good? Yeah.
Did they get simplified even further?
It can get simplified even further, because what is 3 halves plus 5 halves?
8 over 2.
That's 3 raised to the 8 over 2. And what is 8 over 2? Nice. So it's 3 raised to the power of 4. Now it's not a very big number in the exponent, and it's an integer. So we can just compute that by multiplying 3 by itself 4 times. Equals 3 times 3 times 3 times 3. And I think we can walk that out, because what's 3 times 3?
9.
Nice. So there are 2 sets of that. So 9 times 9 is? Awesome. So we can compute that by hand directly without a machine. It's always nice when that walks out. There's another exponential law that I want to develop. It says what happens when you exponentiate and then exponentiate again. And in order to see it, let's see what 5 to the 4th to the third is. Fair enough? So let's first think about what that raised to the 4th, the raised to the third power. What does it mean to raise something to the third power? Yeah, you just write it down 3 times with dots in between for multiplication. So I'm going to write 3 sets of things together multiplied by each other. And each one of those things will be 4 5s in order. So let's write that down. So that'll be, let's see, I'm going to try to give myself enough space both ways. There will be 3 sets of things, and each of them is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. All right. That seem fair enough? Yeah.
So it's 5 to the 12.
So it's 5 to the 12th? Cool. In fact, maybe I'll even write it like this to be extra guiding. It's 5 to the 4 multiplied by 3. Because I see 3 groups of 4 things. That's what multiplication means. Think this works in general? Nothing special about any of those numbers except that they were small enough I could actually write them down. Whenever you see b to the x to the y, that's the same as b to the x multiplied by y. And again, a useful trick that this gives you is you can use this to do a computation directly that you otherwise can't do. So maybe I'll see how people feel. I feel like I've been talking a lot. Kind of like a computation you can just do automatically now? People want me to do? Cool. Do it. Let's hear what you get. component of something actually simple. All right, let's hear it. What'd you get?
3 to the 18.
3 to the
18. Yeah.
That seems bigger than I would expect. Do I hear a second for that or any disagreement? Do I hear a second? Do I hear a disagreement? Cool. Well, okay. What are the other answers that I'm hearing?
27.
27? As in just 27, not 3 to the 27, right? Okay. Because 3 to the 18th I definitely wouldn't want to do by hand. That would get too big.
3 to the 18 divided by 6.
3 to the 18 divided by 6, I hear.
So we're going to do something.
So let's do it then. So in order to compute this out, that'll be 3 raised to the 9/2 times 2/3. Right, multiply this by that. And then fix the legibility issues. All right. So, looks like I just need to multiply some fractions together. How many people would want to just like go on autopilot, multiply the numerator, then multiply the denominator, and then simplify? Cool. You'll make your life harder than you need to, because how do you simplify a fraction? When you write it all out, you try to find common denominators. Common factors. So let's just cancel the common factors now. Do you see anything common between numerators and denominators you can cancel? What do you see? I guess there's the most obvious thing. And so you really just see 9 over 3. Do 9 and 3 have anything in common? Yep, because 9 is 3 times 3. So you can cancel this 3 with one of the 3's from the 9. So this is just 3 raised to the power 3. Also known as 27. So there's one thing you can do. You can use these exponential laws to simplify stuff. And sometimes you can simplify stuff to the point where you can just compute them. Here's another thing you can do though. You can use this idea to simplify things to the point where you can solve them. So let's try to do that. Let's solve the equation 4 to the power of x equals 32. And right now, like, the most obvious thing you would want to do would be like figure out how to undo 4 to the power of x. Which you can, but we don't have it in Boston 4 to the x just yet. We will soon. Instead, let's try and do this. Between 4 and 42, is there like a common base you could see there? What common base is that? 2, I think. It's the only thing it could be, right? 4 is 2 squared. And what is 32 as a power of 2? 2 to the 5th. And if you don't know that, then like you just have to start listing powers of 2, which isn't that bad. 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times another 2, yeah, that's 32. And like, this is really atrocious notation that you should never use on your homework, but when you're working something out scratch walk-wise, that's fine. Because right, I see that tower of numbers now, I have no idea what the fuck it means. Sorry. No. I should be slightly restrained from my swearing in class. Anyway, let's use this. So, 2 to the 2 to the x is the same thing as 2 to the 5th. Or 2 to the 2x equals 2 to the 5th. So between that 2x and the 5, I see 2 different numbers you can put in the exponent of 2, and it gives the same output. But look at the graph at the top of the page. Is that a one-to-one function? Does it pass the horizontal line test? So there are not 2 different numbers you can put in an exponent to get the same output. So that 2 to the x has to be 5. Nope, that 2x has to be 5. Oh, cool. So what's x? Or 5 halves if you like fractions, but it seems like I'm in a decimal mood today, so I'll stick with decimals. Let's do something similar again. 9 to the power x equals 27. In fact, maybe I'll see how people feel. I'd rather you do it and then we come together. Anyone before I do the walk again? Cool, but I will. Those of you who are already doing it might just already be done. So, let's see. 9 and 27, do those have a common base we can use? I think they're all powers of 30. So, let's use that. That 9 is 3 squared, so that's 3 squared to the x equals 3 to the power 30. And now we can use the same trick again. I see an exponential of an exponential. I see 3 raised to a power, then raised to a power. That gives me 3 to the 2 times x equals 3 to the 3. And whenever you see 2 different exponentials with the exact same base equal to each other, those exponents have to be the same. 3 to the x is a one-to-one function. I guess the exception is 1. 1 to the x is not a one-to-one function, as we will see soon. So, 2x equals 3. If 2x equals 3, what is x? Three over 2, or 1.5. If you like fractions, you like fractions. If you like decimals, you like decimals. What if I asked you to solve 5 to the x equals 7? Could you use the same technique for that? Between 5 and 7, is there a common base? No, I mean, like, really, yes, but no. In order to find that common base, you'll need a doodad called a logarithmic function, which is what we'll develop next time. And maybe I'll just see, like, people already have some memories of, like, logarithms. Oh, cool. So you already know how to solve that. We don't collectively in this class right now. We will tomorrow. Nope, Monday. Nope, after the midterm. Monday is a review day. No new content Monday. Cool. So, with that, like, stalling tactic, let's close with a few observations about graphs of exponentials. So here's one. We just developed the graph of 2 to the x on the previous page, and I don't think I want to be super careful about getting it to go through all the points. Its graph looks something like that. Let's use this to get like an opposite. So remember, 1/2 to the power of x, that's the same as 2 to the negative x. So this graph is like the same as that graph, but I put a negative in front of the x. What's that do to graphs? What's up? Over the not y-axis, but the one that does this. It's like even if you don't remember that x-axis is the right thing to say, if you remember like the hand motion, the x values become negated. So the graph will look the exact same as this, but reflected over the vertical axis. And I'm not being careful with points, so don't like. That's not literally the reflection, but it is literally the reflection if I drew the graphs correctly. Fair enough. And I guess that also like makes good sense. If you divide by 2 a bunch of times, because that's what 2 to the x will mean as x gets big, the quantity gets small. If you anti-divide by 2 to the x, that's the same as multiplying by 2 a bunch of times. The result gets big. Cool. How about 1 to the x? What's 1 squared? What's the square root of 1? That means 1 to the 1/2 is 1. What's 1 to the 10,000? Yeah, so what's 1 to any power? All right, you know how to graph that. 1 to the x is 1. Nice. QR code if you want to use it on your own time. It just brings you to a Desmos graph of these same functions. So let's try to do the same thing but with a generic b. Let's try to graph b to the x for absolutely any b. I know what 1 to the x is by the line above. It looks like that. Let's try to figure out what b to the x looks like for every other valid choice of b. And let's start with the generic case that b is bigger than 1. And let's do it by like plotting some points. What's b to the power 0? 1. And this is an exponential, so I expect things to get big quickly. So I'm going to start kind of squished. All right, what's b to the power 1? B, right? That's what b to the 1 always means. And let's see, this case is b is bigger than 1, so b to the 1 will be bigger than 1. If b is between 0 and 1, then there is b. All right, so far so good. B to the power 2, what does that mean? B squared? Cool, so on this side, b squared will be bigger than b, and it'll like scale up. This one will be scaling down. So it sure looks like exponential functions with bases that are bigger than 1 will all basically look like 2 to the x. Exponential functions with bases between 0 and 1 will all basically look like 1/2 to the x. 1 to the x is 1. And let's close with just some quick observations. I've got space right here. What's the domain of every one of these? Oh, well, that didn't work out well. What about the range? Zero to infinity. And did you say include or exclude 0? Nice. And the same there. What about 1 to the x? What's its range? 1 is the only output value it takes. Horizontal asymptotes. Where does this have a horizontal asymptote? Next one? Cool, but they're on like opposite sides. What about 1 to the x? Does it have a horizontal asymptote? I mean, I don't want to say yes. Like, it is really close to a line because it is that line. It has like a degenerate horizontal asymptote because it is its horizontal asymptote. And notice, the last thing I want to point out is that's really different from rational functions. Rational functions have the same asymptotics on either side. Exponentials behave very differently depending on which way you go. Cool. So, there's some extra credit here if you want to like take a look at it. That extra credit will lead you to like where Euler's number even comes from, why it is. Because Euler's number is special because of its behavior with exponentials. But it's special for a way that like is most appreciated by calculus. So in this example, you're going to do yourself some calculus, but I'm not going to say that.
If I remember, this means just trying to remember off the top of my head. 5 log x to the second.
Yeah, close enough.
Oh, okay.
You said all the right things, but it's not all.
Yeah. Yeah. It's been a while since I've done logs, so.
Well, I guess as of Father's Day of next week, that will stop being. We'll use logarithms for an awful lot.
Oh, all right.
Well, no, they're like powerful things.
I have a question with extra credit. So how far back can we go on extra credit before
Beginning of the semester.
beginning of semester, end of semester?
Yeah. I suppose you could do extra credit that like we haven't made it to yet. But I was going to do that.
And then just in your office hour, turn it in and stuff.
Nope, you explained it to me.
Just wait for you, okay?
So, write notes in the extra credit that's like enough that you could tell me all of the laws about why I'm going to do this right.
Okay. So basically, what teaching views.
Yeah.
Okay.
Yeah.
Perfect.
Yeah, the mob what I want to have is like an oral exam where you combine and explain.
Okay.
ask you some things in there detail. I don't